What up, Section 2, Chapter 10. Welcome to the video lesson here on this section. It is a simple essential question that says this. What is a relationship? Not totally the relationship, because there's many other ones, but here's the one in this section. What's a relationship between congruent chords of a circle? Another way to think about it might be this, and it is a good way to twist it, but it's still the same question. What do you think is true if two chords are the same distance from the center of a circle? Now remember, we talked about this. Distance a chord is from the center, and in case you don't remember, here's a little funny haha from the book. It says, this guy here with his little books in hand and this cool little sweater with his stripes across here says, what is the distance from a center to a chord? Great question, you should remember. The lady over here says, psst, it's the length of the perpendicular segment. Haha. And then she throws this out there too, as I would. All you gotta do, dude, is see page 179, problem 15. Bam. So if you need to, go back and look at that, but that is what the distance is. Now here's the scoop. Let me show you how this comes about, because as the question says, what is, or if two chords are the same distance from the center of the circle, what happens? Well, let me make this clear, and what's happening with the picture. Let's say we're talking about distance, as the lady just said. The distance is the perpendicular segment length from the center to the chord. Now I'm going to show you the lengths here of the two distances, I should say, the distances of the chords are not the same. I'll make sure you see this too. The actual angle measures ABQ, that's this angle, and QOC, that's this angle, these guys, they are both 90 degrees. So I want to make sure you're clear on that. That is QB and QO. They are the distances the chords are from the center. So what I'm going to do is make the distances the same, and we're going to see what the answer to the question is in terms of what happens to the chord lengths. Now you look over here, here's the chord lengths. So you can see the chords are nowhere near the same length. AE is much shorter than DC, obviously. American Eagle and District of Columbia, not even close to the same thing, regardless. So let's do it. Let me take the distances and make the distances the same. I'll grab a hold of this point A, and I'll move it over here a little bit. So what I want you to do is I want you to focus on this segment length, BQ. I'm going to make it the same as OQ. That means the distances are the same. And we're going to notice what happens to the chord length of AE in comparison to the chord length of DC. So here we go. Let me take this point A, again focusing on these two up here. Let me take this point A, and we'll move it over. So as you see over here, the chord length, the distance is getting smaller and smaller and smaller. So the chord is getting closer and closer and closer to the center, which it should be. So we're getting closer to this particular distance right there. And notice what's happening over here to the left. The chord length is getting bigger and bigger and bigger. So AE is getting bigger and bigger and bigger. And notice now I'm getting pretty close. So the distances now are getting close. Keep going, look. The distances are almost the same. And when I make them almost the same, check out the chord lengths. They're almost the same. But as soon as I make this exactly the same distance over here, so BQ and QC are now congruent. Let me draw that. So these guys right there are congruent. The distances are the same. What happened to the chord lengths? Oh yeah, check, check. So the actual chord lengths are congruent as well. And I don't even know if you can see that, and that's really cool. Let me do this. Let me make the actual chord really, really big. Notice it's still perpendicular, so it's still the distance. So this distance now is pretty short. Let me make it really short. Let me make the distance like, yeah, I'll make it 1.21. Don't even know if this is going to work. So let me take this distance, 3.58, so QO. Let me make it really, really small by moving D over here. And what I want you to notice, actually I might have to move C too. Move C. Whoa, the whole thing's moving. Okay. Whoops. See if I can get them to be the same. So I'm looking to make these distances the same, in case you're wondering. Hey, look at that. There we go. So there's another example. So the distances are exactly the same. BQ and QC, as small as they are, 1.22 centimeters. Over here, you see the actual chord lengths. Bam! They are congruent. So there is actually leading to a theorem. That theorem is Theorem 78. Let me pull it over here for you. Or no, it's Theorem 77, sorry. So Theorem 77 says this. If two chords of a circle are equidistant from the center, as I just showed you, if two chords are equidistant from the center, then they are congruent. Happens every time. And you use it in two-column proofs, and when you use it in two-column proofs, guys, this is what you write. If you use it in any other type of a question, you don't need to write it. You just use the concept. Okay? So there's that. So now as you see, I kind of reset the picture, and let's converse that theorem, which leads to Theorem 78, number in your book. So here's a scoop. Now instead of saying, let's make the chords the same distance from the center, let's actually do this. Let's make the chords congruent. If the chords are congruent, then what must be true? Your hunch is correct, then they're going to be equidistant. But let's do that. Let's make the chords exactly the same. Forget that I'm not even going to show you the distance yet, or even the angle measure, although you should know that. But let me make the chords the same first. Let's do this. I don't know. Let's make them pretty small. See what happens. Let's make this 502. 502. So let's move this back to make it 502 if I can. If 501, I might have to change something here just to make it work. Sometimes this doesn't quite fly because it's a very precise. Okay, so there we go. So 504, 5.04, 5.04. So the chords are exactly the same. If this theorem is correct, then that means the distance from Q, the perpendicular distance, better be exactly the same. Oh, whoa, that's really weird. That is really cool. Guys, I honestly didn't practice this, didn't try, but what I just did, this is amazing. Wow. I'm proud of myself, thank you very much. But you can see that the chords are exactly the same distance, and the lengths are the same, which is really weird. Alright, I gotta change that. That's just too freaky. So let's move this back. Ooh, let's make it 7.14. So let's make DC also 7.14. That was really weird. How cool. You just witnessed greatness, by the way, guys. Congratulations. I don't know. Let's make it 7. It's not working, so let's make it 7.21. There we go. See what happens. I mean, it's rounding. In case you're wondering what's happening, it's actually rounding. But this is exactly 7.2, 7.2. So the chords are the same exact length. And there you can see, oh, the distances are exactly the same too. That is really cool. I gotta make this work though, sorry. It's just me. Forgive me. You can pause the video if you want. Just kidding, don't pause the video. Bear with me. How do I make this work? I'm gonna make it work. Bye-bye. Ooh, there we go. Bam. Okay, perfect. So now we got it. I mean, this thing rounds. It's crazy how precise the Geometry Sketchpad is. So that's what's going on. But here's a great example. There, 7.63, 7.63. Over here, you see the distances are the same. So there is the converse. And this was, in case you're wondering what was going on, I showed you that the chords, if they were congruent, then that meant this. The distances were the same. So if the chord, that guy right there, was congruent to that guy right there, that meant and it implied that the actual distances were congruent, or the same. So here is Theorem 78. Theorem 78 says, if two chords of a circle are congruent, as I just showed you, then they are equidistant from the center. And here's the scoop. So here's these, here's the two theorems. Here's Theorem 78. Pop that up there if I can. And here's Theorem 77. There you go. So Theorem 77, Theorem 78, they are just the converses of each other. Remember, that just means this. One can go that way, or you can go in reverse. It doesn't really matter. So that means this. Congruent chords, if you have congruent chords, forgive the writing, remember, it's a little funny. Congruent chords imply, beep, beep, doot, doot. Oh yeah, equidistant, however you want to write it. Bam. So, oh yeah, by the way, it means you can flip it around this way too. So if two chords are equidistant, then that means you can flip it back this way. So it is an if and only if statement. Congruent chords imply they are equidistant. If two chords are equidistant, that implies the chords are congruent. Bam! We'll see you in class. Looking forward to using these in two-column proofs and also regular old questions. See ya later.